Hello, this is Mr. Collier, and today we're doing a patterning task called a triangle of triangles. Okay, so let's take a look at the pattern. We got triangle 1 is one triangle, triangle stage 2 is 5 triangles because we have 1, 2, 3, 4 small ones and then one big one, so it's 5 altogether. The next one's 9, so we've got 1, 2, 3, 4 small ones. Then we've got 4 that are one size bigger, and then the big one here is 1. Okay, so that's how the pattern works. And next we have 13 triangles. We have 4 of the small type, we have 4 of the next size, then we have 4 of this size, and then we have one more for the big one, which is 13. So the pattern continues. Let's look at the pattern. The pattern is adding 4 each time. Okay, as you can see, we get a bunch of 4s. We're adding 4 each time. This is going to be 17 and 21. Describe in words what's happening. Well, the number of triangles increases by 4 each time. Okay, use the pattern to make predictions for stages 5 and 6. Well, I already did that. It's 17 and 21 triangles. Justify in words with a diagram. Why would you expect this to continue? So maybe we can do that with a small triangle. When we take a triangle and we actually let's do it the other way around. Take a triangle and you do this kind of thing. To get to the next stage, let me draw it in green. You kind of do this. Okay, so we always add on 1, 2, 3 new triangles plus 1 for the whole thing. Okay, so maybe we could say when going to the next stage, we add on 3 new triangles plus the same size as before, plus 1, maybe we could write that out. We add on 3 new triangles of the same size as before, plus 1 new triangle that is larger. Okay. Next, find the general rule. Well, it's going up by 4 each time, so that should be linear. So the number of triangles is going to be 4 times the stage number, and then plus 1. You can clearly see it's plus 1. Let's see if that works actually. 4n plus 1. Well, that doesn't work for this first part here, right? So it's actually 4. Maybe we can do it this way. Let's do it this way. D. The rule is definitely going to be 4 times n and then plus something else we don't know. And then we can sub in a point. Sub in n equals 1, t equals 1. That's our first stage. So we get 1 equals 4 times 1 plus b. b equals -3. So the rule is t equals 4n minus 3. Or you can just kind of get that visually from the table. E is verify. Verify means we're going to do n equals 5 or n equals 6. So let's do n equals 5. Then by the rule we have t equals, what's the rule? 4 times 5 minus 3, which equals 17. And this matches the value from the table. So the rule is correct. Okay, so that first part is linear. Let's go on to number 2. The lengths of the largest triangle goes in this pattern: 1, 2, 4, 8. Okay, which makes sense. It looks like the size of the biggest one is doubling each time. Okay, it's doubling each time, so it's times 2 this time. Okay, so the length L is doubling each time. Use the pattern to predict stages 5 and 6. So if you have n equals 5, L equals 8 times 2, which is 16, would be the next one. And for n equals 6, we have L equals 16 times 2, because it's doubling. We get 32. Justify why I think the pattern will continue. Well, yeah, I guess at each new stage, at each new stage, okay, a triangle is added. A triangle is added to each side, I guess you could say. You know, each side adds a new triangle. Added to each side, doubling its length, maybe something like that. Okay, assuming the pattern continues, write a rule. So it's times 2 each time. That means for your rule, you're going to have the initial value is 1 times 2 to the power of, maybe it's n minus 1. Let's see if it works for the first one. Let's see, 2 to the power of 1 is 2, so it's not quite it. It's the second one, right? So this means we do need an n minus 1 in our rule. And then we can check it for the second one. It does indeed work. Okay, then we get 2 to the power of 2 minus 1, which is 2 to the 1, which is 2. So it does work. Just remember that this rule could be n plus 1, n minus 1, n minus 2. You just got to maybe check, or you can substitute in something to solve as well. Now verify means we're going to do it for 5 or 6. So let's do n equals 5. L equals, by the way, we don't need the 1 because it's just 1. L equals 2 to the power of 5 minus 1, which equals 2 to the power of 4, which is indeed 16. This matches, I guess you could say, part B. So the rule is correct. Okay, now let's look at the area of the largest triangle. And here's the pattern. They just kind of give it to you here. But you can work this out using Pythagorean theorem. Now you got a root 3 each time. So we're not multiplying by root 3, otherwise this root 3 would cancel. But, well, how do you get from this term, second term, to next term? Looks like you multiply by 4. Okay, and let's check, see what works for the first one. Yeah, if you have this times 4, you get this. So it's multiplied by 4 each time. Okay, so we can say multiplied by 4 each time. Okay. Use the pattern to predict for the next stage. Well, we could do 4 root 3 times 4 is 16 root 3. Assuming this continues, write a formula. The area equals, we're multiplying by 4 a bunch of times. Let's do root 3 over 4 times 4 to the power of n. Okay, so let's see. So if you look at stage 2, by the time you get to stage 2, you've only multiplied by 4 once. So it does have to be n minus 1. Okay, we could have used that logic before, actually. By the time we got to stage 2, it was just multiplied by 2 once, not twice, so that's why it's n minus 1. So yeah, it's n minus 1 in the formula. You can easily test it, and for these 3 values in the table, it does work. Use the formula and previously established results to prove your formula for A. Alright, so let's take a look now what we did before. Previous results, we have the length of the largest triangle. Oh, actually, this is a typo, I believe. This should be area. Okay, that should be area right there. Sorry about that. But we have a formula for the length from before, and we have a formula for number of triangles, which is not helpful. Let's just use the length. So let's take a look. We have, oh, actually, they kind of give us a big hint in the question. Okay, the area equals root 3 over 4L squared. All right, but we have a formula for that. That is from before. We had 2 to the power of n minus 1. Okay, and this is squared, so we just square that. Okay, yeah, so let's take a look at that. We can say 2 to the power of n minus 1 squared. We can use our rule to multiply and get 2 to the power of 2n minus 2. Or, if you multiply 2 to the n minus 1 times 2 to the n minus 1, that's the same as 2 times 2 to the power of n minus 1, which is 4 to the power of n minus 1. And that is a bit more useful because it looks more like a rule. Okay? So I'm going to use that version. So we have root 3 over 4 times 4 to the power of n minus 1. Okay? We have finished proving it. You could have also done it by using this method, but it'll just take a couple more steps.